All right, so this is the lesson 5 practice problems. So just going through these. Number 1 says match each sequence with one of the definitions. So we've got our function definitions, our recursive function definitions down here. They didn't write out the entire thing because if they would have, then it would have kind of given away which each one was. So they're going to make us kind of figure out what the pattern is and then see if we can identify that pattern within our function. So the first one, it looks like we're adding 2 each time, or sorry, let me back up. We're multiplying or adding 6 each time. 6 plus 6 is 12, 12 plus 6 is 18, 18 plus 6 is 24. The middle term, I believe we are multiplying each time by 7. 2 times 7 is 14, 14 times 7 is 98, 98 times 14 is 686. And yeah, it gets big really fast. So we're multiplying by 7 each time. Sorry, multiplying by 7 each time. And then the last one, 160, 80, 40, 20. Looks like everything's cut in half each time. All right, so we're dividing by 2. Or if we look down here, dividing by 2 is the same thing as multiplying times 1/2. And just a quick recap of how this is read. While it says b of n equals 1/2 times b of n minus 1, the way we kind of read it in real words would be our current term is equal to 1/2 times the previous term. Okay, the current term is equal to 1/2 times the previous term. That's what the b of n minus 1 is. That's the term right before, the previous term. Okay, all right. Let's see. The middle one, we were multiplying by 7. I think that's going to be this one here, multiplying by 7. And the first one, we were adding 6. That one goes there. And again, how these last two would be read, current term equals the previous term plus 6. That's what's happening in this sequence. The current term equals 7 times the previous term, which is what's happening in that middle sequence. Okay. Number 2, this one you're given the function and you've got to use the pattern described in the function to get your first 5 terms. All right. Now, what I like about this is they give you a starting point. That's what a of 1 is. A of 1 is the first term equals 7. So we know the first term in a is going to be 7. That's where we're starting from. In the function on the right, we're identifying what we're doing to it. It says the next term in the sequence equals the previous term minus 3. So I take my previous term, which is 7, and I subtract 3, and I get 4. Well, once we identify the pattern, we don't have to look at the function every single time. We know we're subtracting 3 each time. So just keep subtracting 3. 4 minus 3 is 1. 1 minus 3 is -2. -2 minus 3 is -5. Now, we are subtracting by the same thing each time, which makes this arithmetic. Okay? It's an arithmetic sequence. In B of 1, our starting point equals 2. So we're going to start with 2. So the first term, which is what that 1 means next to the B, the first term gives us a solution of 2. Well, what are we going to do from there? Let's see. It looks like our next term equals 2 times our previous term minus 1. So you got to be careful. You could miss that minus 1 on the end there. So it looks like we take our previous term, we multiply times 2, and then we subtract 1. Well, let's do that. 2 times 2 is 4, minus 1 is 3. 3 times 2 is 6, minus 1 is 5. 5 times 2 is 10, minus 1 is 9. 9 times 2 is 18, minus 1 is 17. Now, while this does involve multiplying by the same thing and subtracting by the same thing, unfortunately, you can't have, this is not an example of being arithmetic and geometric, okay? This is not an example of that. You can't multiply and add or subtract together. It has to be one or the other. There are examples of sequences that can be both, but it's because you can say, like we had the sequence 1, 1, 1, 1, 1, 1, 1. Well, we added 0 each time, and that was it, just added 0. Or we multiplied times 1. It wasn't we added 0 and multiplied times 1. It wasn't a combination of the two. All right. So in this case, this is one of those that's a neither. It's not arithmetic or geometric. In C, we start off C of 1, that's our first term, is 3. And what are we going to do here? It looks like our next term is going to be equal to 10 times the previous term. So we just keep multiplying times 10. 3 times 10 is 30. 30 times 10 is 300. 300 times 10 is 3,000. 3,000 times 10 is 30,000. Now this is being multiplied by the same thing each time, making it a geometric sequence. Okay. All right, that's number 2. Number 3, the first 5 terms of some sequence are given, match the rule that each sequence could follow. The nice thing with this one, and these are just written out descriptions of what the functions looked like that we did previously. So I'm going to go up to the top. It looks like I'm going to start down here, actually. I'm going to look, all right, starting at 50, or starting at 1/3, multiply by 3 to find the next term. Well, which one of these starts with 1/3? This one. So just to double check, multiply by 3 to find the next term. 1/3 times 3 is 1. 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27. This is correct. Next one, starting at 50. Well, there's only one that starts at 50. Subtract 25 to find the next term. Yes, we are subtracting by 25 each time. List even numbers starting at 2. That's the top one. Those are all even numbers. List odd numbers starting at 5. I whiffed. Try it again. There we go. There we go. All right, and our last one, number 4. This one, we had 2 graphs of sequences. Now the graphs, it's hard to see, but there's a light blue that goes up like this, and then there's the dark black points that curve up, okay? And they want us to identify, like on term 0, they've already got those labeled for us. Term 1, okay, we got the black and the blue point. A represents the blue sequence, so I'm going to do that first. So at 1, looks like our value of the term is at 2. When I go to term 2, it's all the way up to 5. When I go to 3, we're up to 8. All right, I see a pattern. 2 to 5 to 8. I'm adding 3 each time. Two, 5, 8, 11, 14, 17. Let's see sequence B. Let's see if we got a pattern with this one. Start off at 0, term 0, we're at 1/2. Then at term 1, we're at 1. At term 2, we're at 2. Term 3, we're at 4. I think I see the pattern. We're multiplying times 2 each time. So the next one should be 8. And then 16. And then 32 is not even on this, but I know it's going to be 32 because we're going to keep doubling. For sequence A, describe a way to produce a new term from the previous term. You don't need to write this out in function notation. All they want is a word description here. All right. In this case, we can say add 3 to the previous term. For sequence B, describe a way to produce a new term. Multiply times 2 to the previous term. Which of these is a geometric sequence? Well, the one that's being multiplied by the same thing is going to be the geometric sequence. And that's sequence B. Okay, and the reason why we know is because it's got a growth factor, a consistent growth factor. In this case, our growth factor is 2. Okay. All right, that covers our practice problems. I'm now going to go ahead and we are going to talk about lesson 6. Okay, lesson 6. Now, like I mentioned earlier, lesson 6 is not that different from what we've already been working on. So just follow along and you guys will see how we're gonna talk a little bit more about how we can identify patterns and things like that, and the different ways to represent sequences. Okay, and that's what this second thing says is let's look at different ways to represent a sequence. It says for each sequence below shown, find either the growth factor or rate of change. Be prepared to explain your reasoning. Remember, the growth factor is in a geometric sequence. That's what we're multiplying each term by to get the next one. A rate of change, that's what we're adding or subtracting to a term, right? Remember on graphs of rate of change, it looks like slope because it's going up in a linear fashion. All right, number one, we go 5, 10, 25, 35. We are adding 10 each time, okay? Find either the growth factor or rate of change. Well, this is going to be a rate of change. So I'm going to write rate of change like this. ROC equals 10. And I could write plus 10, but I'm just going to relieve as a 10. That's a positive 10 because it's changing by 10 each time. This is supposed to be 5. I don't know why it disappeared. Starting at 10, each new term is 5 less than the previous term. This one's also going to be a rate of change, but in this case, it's going to be negative 5, okay? Because we're subtracting 5 each time. It's 5 less than the previous term. All right, number 3. Looks like as we go from left to right, we're at 16, then 8, then 4, then 2, then somewhere in there. It looks like it's half as much each time, okay? So this would have a growth factor, and my growth factor would be 1/2 or 0.5. You can write these as decimals, all right? A lot of times we see fractions, but you can write them as decimals. So 1/2 or 5, and that's because when I go from one term to the next term is half as big as the previous term. If we had these written out, it's 16, 8, 4, 2. All right, remember you can take the next term over the previous term and reduce it or use a division. So 1/2 or 0.5. For number 4, this is in function form. I know I start at -5, but that's not what we're asking. We're asking about what the growth factor or rate of change is. In this case, we are multiplying by -2. That's my growth factor. Whatever you multiply by will be the growth factor when that's all you're doing. If all you're doing is multiplying the previous term by a number, that number you're multiplying by will be your growth factor. And in number 5, these are the sequence numbers on the left column. The right column is what's actually in the sequence, 0, 0.1, 0.2, 0.3, 0.4. We're going up by 0.1 each time. Okay, this is going to be a rate of change of 0.1. All right, goes up 0.1. So we're adding 0.1 from one term to the next. All right, we're not going to do all these. We're basically matching. Okay, we're matching sequences to definitions. We're going to do the first, third, and fifth one. Good. So let's take a look at these. So the first sequence, it goes 3, 6, 12, 24. All right, I see a growth factor, okay, because it looks like it's doubling each time. All right, I see a growth factor of 2. All right, so we could say it has a growth factor of 2. Now, if I look through here, there's 2 things I can do. These are in function, okay? These are in function statement, function notation rules here. I know that I'm starting at 3. So which one of these start at 3? Well, there's this one, and this one, all right? So it's one of those 3. I need one that we're multiplying by 2 each time, okay? Multiplying by 2. Well, the only one that starts at 3 and multiplies by 2 is right down here. Okay, and that is M of n. So we're just going to call this one M of n. All right, so we got that one taken care of. All right, so we don't need to worry about that. I'm going to leave that underlined over there. Let's get rid of these. All right, so we got 5 other choices for these other 2. Let's see what we got. Second one, 3, 8, 13, 18. All right, so it looks like I'm adding by 5, adding by 5. I'm adding by 5 each time, okay? So this will be a rate of change of a positive 5. All right, so which one of these start at 3 and then adds 5? So starting at 3 right here. Now h of n says we're doing 5 times the previous one, which that doesn't work because 3 times 5 is 15. So that doesn't work. But the j of n1, that's taking the previous term and adding 5. We want this one. Sorry, I didn't mean to cross it out. We want j. So j of n would go with the second term. All right, our last one here, 18, 9, 4.5, 2.25. Again, if you want to know what this isn't subtracting the same amount each time, but if you want to know what the growth factor is, take the second term over the first term and reduce. And if you want to double check and make sure it's consistent, take the third term over the second term and reduce. That's also going to be 1/2. This has a growth factor of 1/2. So which one of these functions starts at 18 and you're multiplying times 1/2? Well, 18, there's a times 2, 18 minus 5, 18, there it is, times 1/2. G of n is going to be our solution for our third one that we did. Okay? So we should be able to go both ways. We should be able to identify the sequence from the function, and we should be able to identify the function from the sequence. All right, here's a pattern where the number of small squares increases with each new step. This one, I want you guys really to pay attention to this one because this is a new type of sequence, okay? It's a little bit different than we've been working with. So it says, write a recursive definition for the total number of small squares, S of n, in step n. All right, now, the number of squares in step 1 is 1. Number of squares in step 2 is 5. The number of squares in step 3 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, to get from 1 to 5, I'm adding 4. Sorry, plus 4. To get from 5 to 14, I'm adding 9. Now, it looks like what we're doing is we're adding a square onto the bottom of each of these. The first square we added was a 2 by 2 square. Then we added a 3 by 3 square. I bet you the next square we add will look something like this. It'll be a 4 by 4 square, which means there's 16 more that we add to it, which will give us 30 in step 4. Okay? So what we're adding here, 4, then 9, then 16, you guys may recognize these. These are perfect squares. Okay? Let me show you how we're going to write a definition here. We're going to have our initial one. Okay, so we got S of 1 equals 1 because we start at 1. S of n is going to equal our previous entry, so S of n minus 1, so this is the previous term, plus, now here's one thing we can notice. 4 is, what is that? What number do you square to get 4? 2. Well, guess what? We're in step 2. What number do you square to get 9? 3 squared in step 3. In step 4, that's 4 squared. All right, it looks like the step number is what we're squaring and then adding to the previous number of squares. So if our step number is represented by n, I can use n squared to be what we're adding. Okay, so again, we start at 1. Our next term is equal to our previous term plus the step number squared. Okay, and this is pretty consistent. Sometimes it may not be the actual step number. Sometimes it might be the step before squared, or it might be you're looking at the step after, or 2 times the step number. But that's the nice thing about these step numbers. If you have an increasing amount within your sequence, you're probably going to be able to use that step number to help you determine a pattern, a recursive pattern that's going to work for patterns beyond. Okay. Now we're not going to do the sketch today. Now this sequence, they're asking, is it geometric, arithmetic, or neither? While we are adding something each time, it's not the same thing that we're adding. So it's not arithmetic. While squaring a number is multiplying the number times itself, we're not multiplying that times the previous term. So this one's actually going to be a neither. Okay, this fits in the neither category because it does not fit the definition for geometric or arithmetic. All right, I can represent a sequence in different ways. So again, we're not going to do the graph part right now because I think you guys understand what those look like. But if I want to write the first 5 terms in this sequence represented, this is the last slide, by the way. If I want to represent a sequence, again, this tells me what I start with. F of 1 equals 2/3. So I start with 2/3. And then it says my next term is equal to the previous term times 3/2. So here's how, if you don't remember, if you have a calculator, you could probably do this in a calculator. But if you want to remember how to multiply fraction times a fraction, you just multiply straight across. Okay, 2 times 3 is 6, 3 times 2 is 6, and 6/6, that's equal to 1. Well, if I'm going to keep multiplying by 3/2, 1 times 3/2 equals 3/2. 1 times anything equals what you're multiplying by. All right, this next one's a little tougher. 3/2 times 3/2, that's going to be 9/4. 9/4 times 3/2, that's going to be 27/8. Now, none of these actually reduce. The only one that reduced was the 6/6, which ended up being 1. 1, 2, 3, 4. There are the first 5 terms in this sequence. Okay, this actually would be pretty hard to graph because there aren't very many. In fact, there's only one whole number. So you'd actually be kind of estimating your points on the graph as you guys are going. All right. So this is the first 5 here, and that kind of covers the notes for today. There are 4 practice problems that I want you guys to work on.